With that, I'm really happy to introduce two colleagues of mine this week, both of whom I've known for a long time from other jobs as well, and I'm happy that we're all together at Google. So I'm going to introduce John Fonner, HPC Product Manager for Google Cloud, and Adnan Khaleel, also an HPC Product Manager for Google Cloud. Guys, thanks for joining us.
Hey, thank you very much, Jay. It's a pleasure to be here. Welcome, everyone. I'm Adnan Khaleel, and my colleague John is also going to be joining us as we go through some of the content here today. And the topic that we'll be presenting today is optimizing applications and your workload performance and ultimately your cost on Google Cloud. Now, again, just by way of introduction, I've spent a lot of time with on-prem systems, and it's been a learning journey for me, as I'm sure it's for many of you, in terms of understanding how the cloud works, the cloud economics work, how does it matter, from a cost model and so on. So, what this talk really is an encapsulation of everything that I've had to sort of wrap my head around. And I've tried to make it, John and I have tried to make it really easy so that if you're a new user to cloud, and you're looking at cloud, and we just want to make it fairly clear how you get about some of those things. So having said that, let's get started. So yeah, here's a basic sort of outline. We'll be talking about starting from the basics, just an overview of what is cloud, what it isn't, how does it compare to on-prem, some of the economics behind that, then what are the typical dilemmas that a new cloud user faces, and then we'll go into more detail. We'll talk about, the VM types, the different storage options, how do you optimize your pricing and your monitoring your resources and so on and so forth. And ultimately, we'll talk a little bit about AI, but not too much. And again, as Jay mentioned, if you have any questions, put it into the Q&A. And let's get started. Okay, so how many of you on this call today are from an on-prem background, or that's primarily where you sort of grew up? Okay, see, I see a whole bunch of thumbs up. Yeah, and as I mentioned right at the start, same here. I started developing microprocessors for servers, so I really grew up in that environment. And I'm sure there's a lot of users out there who are still predominantly on-prem. So and this is something my wife's grandfather actually asked, is what is cloud computing? Is it really in the cloud? As funny as that might seem, there is a lot of misinformation about cloud. And at a very basic level, the way I want you to look at it is, it is somebody else's computer that you pay to use. Okay, so once you understand that basic sort of concept, things get a lot easier. So moving on, again, at a very high level, what is a cloud computer? Well, you've got some computing infrastructure, and you've got users who can log into that and use it. Now, you might say well, isn't that an on-prem system too? Well, it is, except there's a few differences. Now, the number of users in a cloud computer can change, but and that's the biggest thing, is that they don't all use the exact same hardware as you would in an on-prem system. So what every user does in a cloud computer is they create a virtual cluster based on software, and you can create something that that exactly fits your needs today, and you can create a small instance and you can grow it and then make it small again. But ultimately, it's this notion that you're creating these virtual clusters based on your need. And then, in order to save yourself some cost, you tear it down at the end of your usage. Now, again, bear that in mind, because we'll be talking about that later on. John's going to be going into more detail there. How do you optimize some of those costs? Because it's crucial that you use it for what you need, and then you tear down your virtual cluster, if you will. All right. So again, at a very high level, I just wanted to enumerate a few things that are different between on-prem versus cloud. Now, the cost model, that's the one that everybody's been exposed to starting at the top. It's on-premise CapEx. So you put in a whole, big investment right up front. You design your hardware, and and you deploy it. Yeah, that's the on-prem model. With the cloud, it's different. It's an operating expense. So you can pay as you use. And there's a lot of flexibility there in terms of the hardware, and that gets into the hardware variety. On an on-prem cluster, it's only slightly varied. You may have like some servers that are like large memory, some which have faster processors, some which have GPUs. But when it comes to the cloud, that changes quite a lot because you've got a lot of older hardware that's also available. You have a huge variety in terms of the number of different processor SKUs or storage or accelerators for that matter, and even the networking. So, it's all very varied, and, there's a whole lot of flexibility, and there's a huge amount of choice, but that choice also means that, the cost can vary quite a bit. When it comes to networking on an on-prem cluster, usually it's something very high speed, like, for those who are familiar, like it's either InfiniBand, and it's usually defined during the cluster definition, when you're initially designing your cluster, and from then on, that's what you use for most of your compute connectivity or interconnect. Now, for cloud, it's generally based on Ethernet. So it's may not necessarily be the highest speed, but you do have some high-speed options, and you do have RDMA available. But for the most part, again, because it's all software defined, you can pick and choose. Now, with that, again, placement will vary. Are you creating a cluster with nodes that are close together, far apart? And again, because it's all software, you can sort of put constraints on how you create that cluster configuration. Now, storage, again, and on-prem, it's usually very tightly coupled. It's permanent. So, you have a home directory. You might have some scratch space, based on Lustre or GPFS. And most importantly, you as a user don't have to pay any data movement costs. Like most people, most supercomputing centers don't charge you for any sort of a data movement. Now, in the cloud computing world, well, things are different, as you might have imagined. The storage is very loosely coupled. It's generally not permanent, but you can have, products which offer like some permanency in terms of the data. But the most important thing that you have to be aware of is that there is a data movement cost or an egress cost, right? So, if you're sharing a lot of your data with external users, well, if they download something, well, you have to pay for it. So again, another thing to bear in mind. And in terms, the last one, which again, I think is really the most exciting capability that cloud brings, is that your cluster configuration on an on-prem system is usually fixed. You may have some sort of flexibility to, to do some things differently, but for the most part, it's fixed. With a cloud computing model, again, given the plethora of different sort of processor SKUs and memory and networking and storage, you can actually have an extremely large variety of clusters that you can build. And again, this is all software defined. And typically the way it works is that you would create a configuration for a cluster prior to the job execution. And then once you run your job, because you don't want to still keep on paying for something that you're not using, you tear it down. And again, John's going to go into a lot more detail in terms of the different price models over here. All right, so moving on. Now, for a moment, I want you to one of the things that was really confusing to me is in addition to the wide variety of hardware that's available on the cloud, why are there so many different cost models? And I was thinking about that, and as I was creating these slides, I was like, well, everybody understands the time value of money, right? A dollar today is worth more than a dollar tomorrow. That's one of the economic concepts. And then there is something called, the cost of a future delivery of a product is generally higher than what you'd pay for it today, because whoever's supplying the product, if you say I'm going to buy it 6 months from now, well, they're going to have to hold on to it for 6 months or have some way of producing it when you need it, and they have to account for all of the uncertainty and the holding costs of that particular product. Now, just bear this in mind because it makes sense when I come to the next slide. Now, in the cloud, it follows what is known as an inverted market from an economic perspective. In other words, if you want access to cloud now, it costs more than if you say I need to use the cloud in the future. And the reason for that is, one, it's compute is a scarce commodity. So, typically, like, the demand supply sort of curve sort of comes into the picture. But also, if you're a CSP, what you're doing is you're building extra capacity to meet the needs of somebody who's willing to pay more for access to that compute. So that's why, if I want to use the cloud right now for something, I will use what is known as the on-demand model. And typically, the on-demand model is the most expensive tier when it comes to compute. But if I'm willing to plan, if I am willing to say, okay, I don't need cloud compute today, I need it in a week's time, and the more certainty that you can give the CSP, then they can plan their utilization better, and they're willing to share some of that cost savings with you as a discount. Okay, so that's why cloud costs, if you want to use it today, costs more versus trying to use it in the future, when you've told them that you want to use it in the future. So for a moment, put yourself in the shoes of a CSP, and what you're really trying to do is you're trying to maximize the usage certainty. And really by that is you're trying to maximize the utilization of the cloud so that there aren't any unused resources, because a CSP makes money when the processors are busy doing something. And if it's idle, well, they're not making money. So you really want to maximize that utilization as much as possible. It's not always possible to get the 100%, but there's something interesting that they do over there as well. But ultimately, they're trying to maximize their revenue. Now, when you look at any CSP for that matter, and try to look at their entire compute capacity shown by this, shown by all the different shadings, what you have is at the very bottom, you've got the previously reserved. This is when I tell a CSP that I would like to have some kind of reserved compute capacity in the future. Then there's the next tier, which is the high demand, or the on-demand, sorry, which is also a very high priority, and that is for users who who need compute today, right? And then you've got again, a CSP wants the unused capacity to be as low as possible, but that's not always the case. And there'll always be some unused capacity. Now, what the CSP then does is, because this is all of these things are very elastic, it says, like, rather than just letting this unused capacity go to waste, I will offer that as a product at a different pricing called spot, which is very, very low priority, and you get very high discounts for using this spot. Now, again, I'm not going to go into all of the details. John's got a slide which talks about this. But anyways, but what the spot means is there is a lot of uncertainty for you, because your jobs could be preempted if one of these other sort of tiers come in and they say they need that compute. Okay, all right. So how many of you feel you've got like you're fairly confident in terms of using cloud? Let's just see a thumbs up emoji or something. Like, do you see a few? Okay, all right, and that's exactly what I want to see. Like, okay, so you feel fairly confident that if I were to give you a cloud account, that you would use it fairly efficiently. All right, good. Okay, so that brings us to the next sort of dilemma, and we see this all the time, including myself. So here you are again. As we said, we all started off, we're all like familiar with on-prem. You like it for the most part, but there are times when you have a high priority job that you're trying to do that you cannot get access to compute for, right? Or you need to do some AI training, and you want the latest GPUs, and your supercomputing center doesn't have that. But so that generally happens. Now, so I've just told you about cloud. You feel confident you can do it, and you can go in and you can create a virtual cluster, you can run your jobs, everything is hunky-dory, and then at the end of the month, well, you get a bill and you're like, whoa, this is not what I expected. Why is that the case? Well, in a long-winded way, this is what this presentation is all about. It's about how to make sure that you are not that user on the very right who has that, who's that surprised look of why their cloud bill was that high. Because it is possible if you are not careful. Okay, so and again, the mindset has to be, again, like, and the reason why I walked you through the CSP model, the economics, and all of that stuff is again, there's a lot of flexibility, and that allows you to do very interesting things that you cannot do on an on-prem system. And I don't want you to think about the cloud as either performance or cost, because it's really about performance and cost. And if you know what you're doing and you know how to do it, it can really be a very, very effective tool. And you're not going to be hung up on just the cost aspect of stuff, because there's a lot more capability that the cloud offers. And really, that's what we'd like all of you to walk away from this presentation. Okay, so it's always about using the right tool for the job. And again, as I mentioned many times, it's about choice and cost. So one of the very first things you want to do as a user for cloud is, you have to match the architecture to the workload. There's so many different, virtual machines. There's so many different actual physical processes behind each one of those virtual machines. So you have to find, what is the right sort of SKU or the right VM that you need for your job. Now, obviously, you don't want to use a VM which has a very large memory capacity for a job which doesn't use very much memory, and vice versa, right? That's not the most sort of efficient. So the more you understand your, the needs of your jobs, if you've profiled it, you can pick the right VM for that. Now, as I mentioned, in the cloud model, the networking is typically based on Ethernet. And you have high-speed Ethernet, but again, the placement of those nodes vary. You have to specify that you want to have close placement of the various nodes, so you can minimize the latency and also utilize some of the newer features that we have, like RDMA and so on. Oh, and by the way, the first part of this talk was very, very generic. It was meant to be applicable to any cloud service provider out there. And now we're going to be talking about something that are more particular to Google Cloud, just because that's what we're familiar with, and I can go deeper into that aspect of the actual tools that we offer over there. And so yeah, coming back to networking, there's again, the placement of the various nodes is important, so that's something that you'll have to specify in your software configuration. And last but not least, you've got so many different storage options. How you utilize that storage is also going to be crucial. And we'll talk about some of at the very high level, how do you get started with, starting your jobs or moving your data file first, so you're not incurring any costs, whilst you're waiting for the data to transfer. So with that, I am going to hand it over to my colleague, John, to talk about this part of the presentation.
Thank you, Adnan. And I should pause briefly to introduce myself, since it's my first time hopping on here in this call. My name is John, happy to be at Google. I come from a high-performance computing background. I spent 14 years at the Texas Advanced Computing Center. My background is in the life sciences space. I have a PhD in biomedical engineering, but I've spent a lot of time building infrastructure for people. So everything from training and software to running the cluster within our group, to building platforms and interfaces that let people access resources in a interface that's more user-friendly than the Linux command line, even though I love the Linux command line. So typically, coming from an HPC world, we did a lot of work to try and match workloads to the nodes that we had and to the HPC resources. For an on-prem world, we only want a few types of nodes, keep it simple for the user, get that economy of scale in making purchases. But the cloud really inverts this quite a bit as well. So the cloud is, and what you're seeing in front of you is the node types within Google. Other commercial clouds are going to have different naming conventions, but a similar spread of resources. And even within each of these families that are in boxes here, there are multiple options for how many cores you want on a virtual machine, how much memory you want on that virtual machine. Do you want high memory or standard? So there are a lot of options in how you do it. So instead of only trying to match the workload to the computing resource that you have available, you can start off by looking for a compute resource that's close to what you need. So on the left side of the screen, the N family of nodes here at Google is a general purpose computing. This is great for testing, doing data exploration, a lot of different things like that. There's compute optimized with C. You'll see over on the right side, storage optimized nodes. So they have lots of local storage. They start with a Z. If you're looking for accelerators and GPUs, those are the A and G nodes. And then there's the number that's after them is generally the generation. So it'll go up over time. Higher number means newer. And then also there's a suffix in a lot of places. So for example, at the left side of this pink box, you'll see a C2D node or an H4D. The D there is for AMD. If you don't see anything there, then it's Intel. And A and X can be ARM. So you'll see the A, for example, in the blue box right there, designating it's an ARM processor on there. So this is honestly a tremendous amount of choice that comes out of the box. One of the advantages here that I've been putting to good use recently is just having a greater mix of node types within a cluster or an ecosystem. So if I know that certain problems are CPU bound or network bound or whatever, I can attach the correct node. The other small distinction I wanted to bring up here while we're on it on this slide is that the C family of nodes and H family of nodes are the same chip, same processor, same memory footprint and all that. The H family is optimized for HPC. So it has the RDMA. I know there's a question already in the Q&A feature about RDMA. So that is part of the H series of nodes, which lowers latency on the network connection when you're running a cluster. Okay. So speaking of these HPC VMs, there are a few things that I want to point out. If you're used to on-prem, then you've probably heard of vNUMA. This is the idea of when I run a whole bunch of threads on a single node or have a whole bunch of processes running, how I map those processes to the physical chip. Most of these machines have 2 sockets on them or more that have 2 CPUs on them, and you want to parallelize your code in a way that's using the caches efficiently and always trying to use the lower level caches. So if you're using bare metal, then you're using vNUMA control. On a virtual machine infrastructure, like in the commercial cloud, there is vNUMA. There's a virtual NUMA. And this is making sure that through the hypervisor layer that the virtual machine knows about the mapping and configuration of the underlying physical hardware and will give you a good performant mapping. So that's something that's the default on HPC nodes, which is very reasonable, of course, but very important for HPC. The second one that Adnan talked about, the commercial clouds are solving a lot of problems that require low latency. They require things to be distributed broadly. They require things to be close to the user that's accessing them to be more responsive. HPC has a different problem. We care less about the user getting a quick response, between mouse click or a keystroke and when that hits the machine. And what we really want is for the machines to be able to speak to each other with very, very low latency. So at Google, that's called compact placement. And when you're launching VMs, you can request compact placement, and it will put them close together physically on the same network. And that way, when you start to do things that require multiple nodes in parallel, you'll have what you are expecting there. And then finally, the network optimizations. The big one for Google is RDMA. Amazon has a different name for their high performance over Ethernet. There are nodes in the Azure cloud that use InfiniBand. At TAC, we use InfiniBand, so that's the out of the hardware level low latency interface that you can use, which is also very good. Okay, so this is some of the considerations when you're talking about the CPU and GPU, the network, the controls there, but we should probably talk about storage. Adnan, I'll let you take it from here.
All right, thank you very much, John. So, one of the very first questions, I had when I was beginning to create my own clusters and things of that sort in the cloud, GCP, is how does one go about moving data, and what is the best practice when it comes to moving this data, right? So before we get into that, what I quickly want to show you is, again, because everything, there's a cost associated with every sort of option you pick. when it comes to compute or networking, even when it comes to storage. I wanted to give you a high-level view of how those costs are stacked for the different types of storage. Now, if you look at this pyramid at the very bottom, you've got Google GCS, and that is more of a persistent archive kind of a thing. It's not the most performant. It's based on an object store sort of storage model, and it's the least expensive of your options. Above that, you've got something that's a bit more persistent. That's shared. That's Google File Store. Think of it as, you know, a cloud-native NFS sort of a file system. Then you've got, you know, your scratch file systems, typically, you know, Lustre or GPFS. You know, when you come from the HPC side of the world, but it could be, you know, some other options as well. And then, you know, the last one is you could, if your job is restricted to a single node, well, you could use a local SSD on that node. But the one thing to bear in mind is that's sort of very, very ephemeral. So the data you put on the local SSD is generally lost as soon as you tear down that node. So, and you know, in order for you to preserve your data or to use it more effectively, you know, using one of these other sort of storage options is probably a better choice. Now, let's say you're a user that's used to running something on an on-prem system. Now, typically, again, as I mentioned earlier, you don't have any data movement costs. In other words, you know, you had your data in your home directory most likely, and then you could probably access it from your compute nodes or you know, typically. But in the cloud, you've got to do things differently, especially if, you know, you're using a mix of on-prem and cloud. So typically what you would do is you would create a bucket in GCS and copy your file over. That's the very first thing you would do before you even create your virtual machine. And part of the reason is, you know, you don't want to pay for that virtual machine when it's not being used. So in other words, you know, you create a bucket in GCS at the very bottom, you know, you move your data over there, and then, and you know, if it's a very large data file, that can take, you know, a substantial amount of time in some cases. What you do next is then you create your VM. You can launch one either like, you know, Google Fuse and mount GCS, or you could use one of the 3P solutions that are out there. So that way, when you launch your job, it's not waiting on the data anymore, and you've optimized your cost such that, you know, the data is already there. It's not waiting for the data to come, and then as soon as your job is complete, you know, you can, you know, tear down that VM and move on from there and avoid being charged for, you know, for that compute cluster. All right, so one of the most important tools that I've found as I've gone through the journey myself is, you know, trying to understand the pricing. Now, you know, as John and I have mentioned several times, you know, each one of the different options has a different price, and it can get quite hairy if you don't, you don't know exactly what you're doing. Now, luckily, there is a tool called the Google Pricing Tool that you can go to that particular URL over there, and you can create, you know, or recreate, you know, what your compute engine looks like. You can, and that's exactly what I'm going to show you over here at a very high level. So just to make, you know, make this a bit more concrete, let's say I have a 4-node Slurm auto-scaling cluster using H3 VMs, like one of the VMs that John described earlier. That's fairly high performance. It has 50 terabytes of Google file store for scratch usage and about 500 terabytes of GCS for home. Now, you'd have to sort of put all of these details into the cloud pricing tool and to get your price. So the way that works is, actually, I should have mentioned. So you look at this like over here where my mouse is, like, you know, add to the estimate. You click on that, and then it's going to come up with a bunch of different resources that you can price out. And in this case, we want to price out the compute engines. So when you click on that, it'll have these drop-down boxes for, you know, the number of instances, the types of those VMs, you know, and you have a few other options there. Are you using all of the cores on that node or not? And you can also ask, what is the pricing model? What is the provision model that you are looking for? Now, on demand, this gives you access to the compute right away, as if you go back to the earlier part of this talk. And once you've configured all of that, you can say add to estimate, and then you can move on to adding the other resources. So in this case, we want to add the file storage. Similarly, you can go back to this, add to the estimate. You can put in storage in the search box. It's going to come up with, a couple of different, well, several different storage options. Pick the ones that you are interested in. In our case, we are interested in file store. That's kind of our scratch space. Click on that, put in the details, which is, zone 1. It's it's based on an SSD. The capacity is like 50 terabytes. You add it to the estimate. And similarly, you can do the same thing for your other cloud storage, which is, this box over here. Ultimately, when you do all of that, you can get, the different, you've built your configuration in the pricing tool, which allows you to then get a price. Now, the other thing that I mentioned is if you don't want or don't need to use the compute right away, you can use the spot, which is the preemptible version, which is the most discounted version of the VMs. Now, initially what we had done is we had said we wanted on demand, but what we're going to do now is say we would like to use the spot version of that. Now, a few things to bear in mind when you use the spot VM is that your jobs are preemptible, because if somebody with an on-demand or a reserved usage needs or is going to want that resource, well, guess what? It comes out from the spot pool. So even if you have a job running, typically you get some notification to your Slurm manager that this VM is going to go away in a couple of minutes. So you better sort of like checkpoint and kill your job. And that VM is going to wait. But based on what sort of Slurm manager and policies you have, that Slurm manager will look for another spot VM that's available and launch your job on that. But that is the sort of the trade-off that you have when you use spot, is that you don't have any guaranteed usage. You get a huge discount for that, and not all jobs are amenable to this sort of a usage model. But if you can, this is a great way of saving costs. Now, for the next section on the different consumption models, I'm going to hand it back to John, and he's going to talk to you about, what are the different pricing options here.
Yeah, thanks, Adnan. So Adnan mentioned some of these. When you think of cloud, a lot of times it's just on-demand usage. A lot of times this is the price that is listed on cloud websites as well. If I want to fire up one or many VMs, I can do it right now. They'll start working on it, within a few minutes. I'll have it up. And that's sort of this on-demand box on the far left. There are a lot of discounts to be had to save money, especially if you're moving your computing footprint largely to the cloud. One is committed use discounts. The idea here is that if you need a steady state footprint of compute capacity, then committed use discounts, which are usually measured like 1 year, 3 years, they can be longer, they can be shorter, but those really give a deep discount on the cost that you're paying per hour and can make it a lot easier to have persistent footprint in the cloud. This idea of flex CUDs, the other cloud, by the way, these top 4 boxes, they're the same across cloud providers. They all have different names. I think Amazon calls them reserved instances, but they're the same idea. We call them committed use discounts. So flex CUDs commits to a certain amount of spend. So I know that my footprint, my ongoing footprint has a certain value attached to it, but I want to be able to change which node types I'm using as I go. So flex CUD is really meant to support that. You may not always be using an H4D, but you have a footprint there, you have a constant need, and then you can switch to whatever node type is most amenable to what you're doing. Spot VMs are exactly what Adnan described in the last slide. They have a huge discount if you could take advantage of them, but they are preemptible. The idea is that you get, it's between 30 seconds and 2 minutes, depending. a notice, a signal that's sent that you can pick up within your script that will tell you you're about to be preempted, and then the job will terminate. Graceful termination, because you have this warning, and you can write a checkpoint file, you can do whatever you need to do, you can go start, to trigger another job to continue the work. So if you have the infrastructure and the flexibility to wait if your job gets preempted and then come back to it and finish, then it's insanely cheap to use Spot VMs. You're making it easy on the cloud to manage its resources, and they're making it easy on you. So it's the last two boxes that are a lot of fun. This is, we call it the dynamic workload scheduler at Google. And you can either flex start virtual machines, where you describe the resources that you want and let Google choose exactly where those land and exactly when to deploy those. That's especially useful for resources that are under high demand. A lot of GPUs are under high demand right now, for example, or TPUs in Google's case. And then there's also a calendar mode. So if you know in the future, I'm running a workshop, or I have a class or something that I'm doing, you can go to Dynamic Workload Scheduler and say, I don't want these nodes now, I want them in the future, and you can reserve them. And that also comes with some pretty good discounts. So on the next slide, I'm not going to spend long on this. There are online tools for budgets. Adnan mentioned in the second slide, we don't want any surprise bills for anyone. We want people to be able to plan around their needs and have those met. So there are budgeting alerts that you can do if your workload is bursts a lot and you don't have good predictability in what you're doing. So the last piece that I really wanted to talk about for my section of the talk is we talked about picking the right nodes to match what you want to do in the cloud. There's this other side of, how do I know that I got it right? And this is observability and monitoring. Many of you will recognize the screenshot. Give me a thumbs up if you already know what this is. But Linux has a lot of traditional tools to be able to take an instantaneous peek at what the node is doing. It's looking at the hardware to see what the CPU utilization is, memory, the bandwidth that's going to disk, the bandwidth that's going over the network. So this is BTOP that's there. Top, HTOP are alternatives. They're all just slightly different views of it, but it gives you an instantaneous status. A lot of times that's very valuable. If you're in there, you're kicking off a job, or you're kicking off a script, and you just want to check to make sure it's using all the cores, things like that, then something like that's a great tool. And that's available anywhere. Top itself is built into most Linux distributions. There are other more specialized tools that either do job level monitoring or cluster level monitoring. The ones I've listed are all on GitHub and open source. And those are things you can do when you don't want to be physically present looking at your screen. You want things to just run for a while and to be able to go back and look at them. And the goal here is kind of these two questions that are listed in the bottom. So we think of traditional HPC jobs as being bound by the processor, either the GPU or CPU, but a lot of workloads. I mean, I come from a life sciences space, so especially in life sciences, we may be bound by how fast we can pull files from the file system and read them in, or we may be bound by how much memory we have on the node. So it's important to have a compute node that has a lot of memory, because we want to do all this data comparisons in memory. Or if you're using traditional MPI, then there's a step where there's like an all-to-all communication over the network, and you want to see how much delay is that creating when I'm communicating over the network. So those are all the pieces that we're using this type of tool to look at. And if we see something that's an obvious mismatch, I'm never using more than half the memory, or something's going on with my threading, or when I burst out, my performance goes down, what's going on with the network, then this is how to get that information to be able to troubleshoot it. There is, at Google, there's a nice alternative as well that I have enjoyed discovering and using, that there's cloud observability. So when you launch an instance, you'll see this observability tab that's pictured. It's available all over the place. And it does a good job at showing you a lot of the basic hardware statistics that you would be looking for to make sure that your workload is doing well. The polling here is once a minute. So if you're seeing memory spikes or something like that that's at a smaller time scale, they may not show up here. But in general, and for most things, this is fantastic. And it's also great because you can, the amount of time, which is kind of top right on that screen, right now it's set for last 12 hours. You can change that to be something very short or something very long. And so if a little time has passed between the event that you want to look at. And now you can actually kind of go back and look and zoom in and see how things are going, how all the nodes are interacting with each other. And it turns out, this is the most fine-tuned use case, but it comes up a lot as being valuable. The last thing, this is Google specific as well. There is an active assist recommender. So you can go to the recommender and it will look to see how well things are mapping to your utilization. All right, Adnan, I'll hand to you.
All right. Okay. Thank you very much, John. So this wouldn't be a Google talk if we didn't have at least one mention of AI, and then that's what this one slide is. And and really the thought behind this is that even though we're all trying to do HPC workloads, there is an opportunity to use AI in order to make your entire computation that much more efficient, especially if you're doing it in like phases where you can have a phase of HPC followed with some sort of AI training leading the next phase, and so on and so forth. And Google has a lot of tools over here that you can utilize to do something like that. And Vertex AI, if you're not familiar with it, I'd highly recommend that you go and look at it, because it allows you to do exactly that. It allows you to create surrogate models based on your HPC workload that then allows you to have this sort of mixed sort of mode usage in order to do more computation, more problem discovery and solving with the same amount of computation. Now, the next one is Gemini. All of you are really familiar with, at least I hope you're familiar with Gemini. And it's amazing to see the advances and the improvements that the team has made, even in the short span of the 6 or 7 months that I've been here, and things, right from idea generation to really having, to do some of the coding and being an active member of your sort of science discovery team. And that's really what excites me, is when you look at all of these tools, not just in isolation, but in tandem, they are really very, very powerful. The next one is Gemini CLI, which I think is really amazing because, at a very high level, people will say it's like a command line version of Gemini, but I really don't think that does it justice, because it can really go beyond that. And you can give it a simple prompt, like I would like to create a cluster in Google Cloud based on at 4 node using Slurm, auto scaling, and it'll figure out everything that it needs in order to be able to do that. All you have to do is provide, obviously, your Google ID and your billing information. But once you do that, Gemini is actually smart enough to figure out everything on its own, and I think that was, to me, quite a revelation. So I really invite everybody on this call who hasn't tried it to go ahead and give it a go. And again, lastly, just to tie everything together, it's really about moving beyond just cost per hour, which we're so used to thinking about in terms of our day-to-day work, especially when you're using the cloud. Think about it more of a cost per discovery. And when you integrate all of these AI tools, you can really maximize the value of that dollar that you're spending on the cloud. Okay, so to tie everything together, and as John has mentioned and I have mentioned, you have to pick your infrastructure based on your needs. So be careful of what you pick. With great power comes great responsibility. So as I mentioned earlier, is pick a VM that makes sense for your particular workload. The next one is the consumption models, as John pointed out. Between on-demand, CUDs, flex CUDs, and spot, you have a lot of variety of what kind of discounts you can make use of. So if your job can wait, I would highly recommend you go for some sort of future reservation model, or one of the CUDs or the flex CUDs. If your job is preemptible and can withstand the abrupt sort of endings, spot is a great option as well. The next one, I cannot stress enough: when you're not using your cluster, tear it down, because as long as your cluster is up, you are paying for it, whether it's running your job or not. So one of those monitoring tools that John talked about, or even some of the alerts, those are actually useful in making sure that you don't exceed, how long your cluster is up. All of the dashboards that John has mentioned, the GCP monitoring tools, get to know them and start using them along with some of the Linux tools like Top and, as well as, they are there for you to understand your workload. And all of those can help you in minimizing your cost. And lastly, but not least, if your job can make use of AI, you should start seriously looking at that as a possibility and trying to integrate everything together. All right, so I think I have just one last slide before we get into questions, Jay, because I know I see Jay being really, he's being eager to ask the questions. But anyways, what I would suggest is, again, if you haven't used Gemini CLI, go ahead, start using it today. Try to create these clusters. And, if you feel like, you've made plenty of good progress there, that's great. But we are also available to help you become successful. So feel free to reach out to any one of us, Jay, myself, John. We're here to make sure that, it's easy for you to get started. And we want you to have a great experience as well. And the other thing that, we're doing is we're having these workshops that you can participate in, and we're going to have them, multiple times over the course of the year in different locations. So if one of them happens to be convenient for you, please do join us. We'll be talking about some of these things in more detail. And lastly, but not least, if you'd like to work on a proof of concept, again, get in touch with us. We'll work with the go-to-market teams and some of the subject matter experts and help create a proof of concept that really works for you. So with that, again, thank you very much for all of your time and attention. And Jay, I'm going to hand it back to you.
Great. Thank you, guys. Let's give John and Adnan some applause with that meat emoji at the bottom. There are only a couple of questions submitted to the Q&A feature, so I think we have time for both. I did just want to make one sort of summary statement for our audience here. I think John and Adnan did a great job of explaining the different cost options for this in terms like tearing down. One summary line that I might add to that is cloud computing has a perception, and I would argue a misperception, of being really expensive, because people tend to look at the most expensive cost, the on-demand cost. But if you think about the cost to run a 100 GPU job for one day, that is a cost. But to do that on-prem, you'd have to buy the whole cluster and do that. So you have to compare apples to apples, how much time you're going to use, and compare that to the cost of the resources you require to do it. The cloud gives you this ability to, and all cloud providers give you this ability to pay a premium for a very small amount of usage or for on-demand usage. And then, just as with on-prem, give you a much better cost for extensive uses, for committed uses, and also for non-urgent uses using spot techniques. So there's a variety of ways that all cloud providers can really bring those costs down based on amount of commitment to use, using it in the background when it's not being used, things like that. And that really, those are the things that you should compare to on-prem as opposed to just the single job on-demand cost, because that's a very different ball of wax right there. The other thing that I would really, it's always frustrated me, John and Adnan, the phrase tear down a cluster. Really what you're doing in a cluster is you're assembling the resources and integrating them into an HPC cluster in a cloud, and then you're releasing the resources back to be used by others. So never really understand how that tear down phrase got used, but all that means is you're assembling the resources with software to become your cluster, and then you're releasing those resources again. So that somebody else can use them, maybe for completely different things, maybe also for a cluster. So with that, we will go to Q&A. And whoops, I'll save that slide for next. Let's see. Caden Ellis asks, how are people handling data locality with price minimizing on hybrid setups? We have a lot of data on-prem, so bursting in the cloud might need a lot of upload. Or conversely, if a job in the cloud generates a lot of data that ends up on-prem, generates a lot of data that will end up on-prem, that's a lot of egress costs. Any clever solutions?
Yeah.
John, do you want to?
Here, I'll dive in.
Yeah.
First of all, the cost for data movement in the cloud is really the egress side of this. Ingress is free because the cloud wants you to put all your data up there. So if you have a lot of data on-prem, then the strategies that Adnan talked about, where you create a footprint for that storage first so that you can move it and then pay for compute once the data is already close to where the compute is, that's the efficiency there. I mean, I would say it's a pretty standard strategy. It's really good. On the egress side, there's a couple pieces there. One is don't copy everything. Only copy the output that you care about. You know, in genomics, for example, the output is much smaller than the input. In simulation, it can be inverted, but again, make sure it's compressed. Like, there's lots of little tricks you can use just to be efficient. The other piece is that I want to mention, because my bleeding heart is for science. I want Google to be the best place to do science. For universities and public institutions, essentially Internet 2 connected areas, there are programs that waive egress costs. So talk to your university or talk to places like that. Mm-hmm. And as long as, I don't remember the details, it's something like as long as the egress cost would be 15% or less per month than your compute bill, they don't charge you anything for egress. So if you're committed to this model, then you can just bypass it completely.
Oh, and the one thing I might add to that, and John, you know, what you mentioned just kind of reminded me is, you know, for public sector, there's a lot of incentives. So make sure you reach out to one of us and we can connect you with the right folks. And in some cases, you know, based on, you know, the nature of your research, there's some waivers available, there's some other discounts and so on. So yeah, so make sure, even if you're using the cloud, feel free to reach out to one of us and we can connect you so you get some of those discounts, which you wouldn't otherwise.
Yeah, I like that answer. There are smart techniques you can use to minimize the amount of data that you move back and forth. There are different workloads have different data movement costs anyway. As John mentioned, some simulations don't produce as much output as like some genomics data analysis, for example, doesn't produce as much as some 3D CFD simulation. So think about which workloads to run where when you're doing that as well. But of course, it's always what you can negotiate. So when you're doing a CUD or a flex CUD or something, especially if you're public sector, look for incentives and opportunities there. Last question, and we need to answer this one really quickly, is from Diarmid Buckley. On topics like InfiniBand and RDMA, any thoughts on what is the state of the art on RDMA over Converged Ethernet, which has high performance? John, Adnan, anything you want to say quickly on that? I think that's a longer topic. Right?
Yeah, that's a really long topic, but John, why don't you go first?
I can be brief. InfiniBand is the fastest right now. It has the lowest latency. It is the most expensive. Things like RDMA have, well, they're proven, at least to me. I've been running benchmarks and actually know one of the guys on the call is running benchmarks. They're getting better over time as well. They are a lower cost implementation that moves some of the heavy lifting to the network card. This is a trend you'll see across computing. I believe Converged Ethernet is very similar in its approach, so using the existing wires to be faster. So InfiniBand is faster but more expensive. Just look at your workload. If you're not going out to thousands of nodes, you'll probably find that one of the other two options is maybe better price performance.